Hello and welcome to the session entitled Florence AI, Reinventing Data Science at Humana. My name is Dave Mack, and I'm a cognitive and machine learning principal at Humana in the Digital Health and Analytics organization. Today, I'll be walking you through some key aspects of how easy it is to build a model on the platform I've helped create over the past 18 months. I hope that you can learn something new to take back to your organization. Humana's bold goal is to address the needs of the whole person. This member-centric view is part of our commitment to help our millions of members achieve their best health. A Fortune 50 company, Humana has a breadth of resources available, and we've recently invested significant time and money into fighting the COVID-19 pandemic, food insecurity, loneliness and social isolation, and inequities in healthcare, to name a few. Humana has also made a significant commitment to digital health and analytics, forming a top-level organization led by Heather Cox in 2018, so that through advanced analytics, experiential design, data, and technology, we're working to meet our associates, members, and the communities we serve anytime, anywhere, and anyhow. I've been privileged to be part of Humana since late 2015 when I started in clinical data science before helping lead Humana's transition to the cloud. Our platform now supports hundreds of users, taking advantage of the flexibility the cloud brings. Florence AI is a cloud platform for automating and accelerating the delivery lifecycle of data science solutions at scale in Azure. Its name was inspired by the historic city of Florence, Italy, and all the amazing things that went on during the Renaissance there. While we're not building innovative contraptions to lift bricks and stones to new heights like was done for the Florence Cathedral's dome, we do get to build some cool stuff with Databricks, PySpark, MLFlow, and Azure Data Factory, while supporting many of the most popular libraries for ML today. The ecosystem empowers data scientists to solve complex problems, promotes access to open source innovation, simplifies model consumption with a single interface, all while trying to transform workflows to improve performance. Today, I'll be touching on many of the key foundational pillars you see listed here. The model is really nothing with terrible ingredients, so we have to have some good things to start from, and from that, we have our feature store. It has tens of thousands of features available for training and scoring, with hundreds of instances across multiple years ready to use for data scientists. It's flexible to cover most use cases, but specific enough so that custom situations can be handled through self-service operations using the same code. We put a lot of domain expertise into the feature design that's been pre-computed for the entire population and is refreshed regularly at monthly and daily cadences. We have extensive metadata ready for the data scientist to understand and learn about the features, how they were created, and what they mean. We support them through the whole lifecycle, from cohort design through the initial feature selection, and then into the model training experiments, where they cycle through and find the best model. Once that's done, they score and register that model and record all of their training artifacts to make sure that their work is reproducible. We then work with them to develop the scoring code and testing needed for their model before we promote it to production and automate the scoring on a regular basis. I'm going to be using an example problem today to help trace the workflow through this platform so that you can see how a model is built today. We're going to predict the most severe stage of chronic kidney disease in the next 6 months. This is an important chronic condition because as members progress through the disease, if they crash into the later stages, they can get to dialysis much quicker and have a lower quality of life. We want to delay that as long as possible, and that's why this is an important problem to solve. You can see some of the criteria that I used to define the cohort here, and I've built up a set of members that have different stages. You can see that we have a pretty imbalanced class set here, which is a common problem in healthcare data. Let's see how we can build this model on the platform today. So first, we'll start with our initial feature selection and do some basic model training. So I'm going to be walking you through a notebook that we have that's a template that the data scientist can start from to do this feature selection. Our goal is to get down from the tens of thousands of features we have in the feature store and any custom features they create, down to a few hundred features. So the initial feature selection template here is a Databricks notebook, and we have some of the initial things installed and the imports made. We also have a few different parameters set up. From there, they can load a combination of feature stored data and their custom features. There, we'll split it into a train and test set, and then compare the distributions of those two things together to make sure that these things are similar. After that, we'll do some basic prep to categorize them and look at a few things that are basic to eliminate some features early. So we'll take a look and see any that have a single value or high percentage of nulls and exclude those. And then we'll do some final formatting before we get ready to do the pipeline of the model. Before Spark 3.0, there wasn't really an easy way to do the string indexing with all the columns at once. And with tens of thousands, potentially, we had to roll our own to make that happen for our users. After the indexing step, we get to a typical Spark pipeline to do the prep before we get into the feature selection. We index our target, one-hot encode our variables, along with imputation for our numeric variables, and then bring them into a feature vector. From there, we give data scientists the option to use different aspects of feature selection. I chose a random forest classifier here with 25 trees and fit that model to my index data. After that, we have a helper function to help them extract those feature importances out of the random forest classifier and sort them in a pandas data frame so that they're going from most important to least important. Then they can display that and walk through those features and see if they make sense. We can then use a pretty low cutoff to get down to hundreds of features for our first round of modeling. The process and transform features have slightly different names, so we use this block of code to get back to the original feature descriptions. Then we can save those data sets out and go on to the next step. And there we'll do our first round of modeling using Spark ML. We have a simple helper function to make the creation of the MLFlow experiment consistent for each user. We also have created a separate helper function for the Spark training. We do this in a similar prep fashion to the initial feature selection. And we can see here that we're inputting a cross-validated estimator and a parameter grid to do the search. This gives us a wide variety of options to be able to parameterize these for any type of cross-validated Spark model. After we do our experimentation, then we'll arrive at a best model. We can see at the top here that we have different parameters from that best model, and we'll have their estimator, in my case, a logistic regression, that came out to be the best model. We then have a different helper function that allows us to be able to do a few more detailed things about our model. It even generates a heat map. This is important because we could have just had a majority class classifier and had a high accuracy. But this heat map shows us that when we used our class weighting, we ended up getting pretty good predictions along the diagonal, though we still have a little bit of over prediction in our majority class. And there's a little bit of a problem in the middle here with some of these mid-range stages. Let's take a look at the details of these Spark helper functions to see what's going on behind the scenes. So this experiment utility has a couple of the helper functions I referred to earlier in the notebook here, our MLFlow experiment creation and our feature importance extraction. Here's the Spark ML setup with our cross-validated parameter grid search. We have this function here where we start our MLFlow run, fit our model, and grab our test predictions. From there, we'll log the metrics that come out of our test set. And then we'll also grab our training metrics from each of the cross-validated parameter runs. We'll grab those parameters as well so that we can graph them in a bar graph format to plot the different accuracies for each run. We'll then save that figure out to the MLFlow run, along with the best parameters for the model and the model object itself. We'll also write that to ADLS for backup. For the best model, we go through and do similar things here, starting our MLFlow run and fitting our model. But then we'll score it on the full training set and test set, log those metrics and the best parameters of our model. And then if this were a binary classifier, we might create a rock curve. But in this case, it's a multi-class classifier, so we're going to create that heat map you saw earlier. From there, we'll log that model out and back it up to ADLS as well. So with that, we can really encourage reproducibility with this reusable code. We automatically save many items in the MLFlow run, and that's all workspace scoped and can be seen within that particular user's workspace. We also ask them to save several artifacts out to help make their model reproducible, like input schemas, training and test sets, and the scores associated with those, along with anything they did outside of the pipeline for feature prep. These can be used for scoring later. So now we're not done. We've just kind of done the first round of modeling. And now we want to take a look to see if deep neural networks can help us at all improve the model. Those that may not be familiar with deep neural networks, they have similar inputs and features that we bring in, but then they have a series of hidden layers that help work together to explain the relationship between the inputs and the targets. That'll generate our predictions, and it does so over repeated passes called epochs. These continue to learn each time we go through to make the model better. There's some extra things we need to think about when using deep neural networks. We want to use early stopping to minimize our training time when diminishing returns happen over multiple epochs. We can use callbacks to log things after each epoch. And we can also do it on smaller chunks of data to make sure it's working the way we want and allow us to scale up later once we refine our parameters. We can do this initial searching with a tool called HyperOpt. This allows us to define a parameter space that's pretty generous for us to search. And we have a couple of different ways to go about that search. We could do one at a time with a full Bayesian, or do full random, or something in between. In my case, we're going to do the full Bayesian to learn from each run. So you can see we did 20 trials of our model, and the loss improved each time. But we want to probably look at those to see if we get a sense of what kind of models are working best, as we're using a sample of our training data. Thankfully, MLFlow has a handy parallel coordinates plot where we can take each of our parameters and graph them against the best validation loss for each run. We can then see, in this case, we're highlighting the first time, in the first layer, we have a set of complex nodes here. If we have that set up, and then we look at layer 2, we see that complex set of nodes here doesn't work very well for our model. But if we have a simpler set of nodes here, that does work pretty well with a lot of runs. Also, we see that a low learning rate and high batch size is important. Now that we've done some initial exploration on the driver, we see that we were running pretty fast for each epoch, but we were only using a small fraction of our data. If we scale up to 10 times the amount of data using Petastorm, we're running at about 10 times the length of time, and that can take a long time. So let's bring in Horobot to help. Horobot allows us to use all of the data, and we have 16 workers here, and we can get down to a pretty similar time we saw before per epoch to help us train on all the data much more quickly. It's 4 times faster than just using Petastorm alone. Let's take a look at how we can set up Petastorm and Horobot to run in a template. So this template here, we have all of the imports here, and we have a similar setup to how we did the initial feature selection in our Spark ML training. We create a train and validation set and compare those distributions, and then do a lot of the same feature prep that we used in Spark. In fact, we'll use that Spark ML pipeline, and we'll transform that after creating our MLFlow experiment. From there, we can separately train the rest of our model more easily. We'll apply our class weights and do a little bit more feature prep by encoding our target so that we have data in the right format for TensorFlow. We'll also set up our Petastorm files, and then we'll create our actual neural network model here with a couple of hidden layers and a couple of other parameters. And the user can customize that to their needs. From here now, we have our helper function to set up our multi-class classification for TensorFlow and Horobot. You can see that I've chosen parameters from what we learned before, where we have a complex first layer and a simpler second layer. We have a small learning rate and a bigger batch size. They can also manipulate these pretty easily for each run. But let's take a look at what this helper function does for us here. I'm going to jump down here to this. This helper function is set up similar to what we saw before. We'll have our MLFlow run start, and we'll log some basic parameters for our hyperparameters. From there, we'll use the Horovod runner to train our model. Let's jump down here to see how that works. So here we have to bring in some imports due to some serialization requirements. Then you can see we're converting our data into the format that we need for TensorFlow to work. We're also then scaling our features and using the encoded label here so that we can get that data set up to run. We'll add in the early stopping and our optimizer, and then here we'll add some metrics for multi-class classification like precision and recall before we compile our model. After that, we'll go through and create our checkpoints and then our callbacks. The callbacks are important because that allows us to log stuff after each run. It's important to set this to only happen on one of the workers here, because otherwise it's going to be logged 16 times, and we don't want that duplicated. We'll then go through and fit our model, and you see we're only writing out information intermediately each time we go through the epic once. We'll then also save our checkpoint weights only once as well, and copy that model over to DBFS. Jumping back up, here you can see that after we fit our model, we can go through and grab that metrics history and log all of our individual metrics from each epic. And that allows us to be able to generate graphs pretty easily on MLFlow to look at our learning curves or other things you want to see from the model training. We'll then log a few other things like the model structure and the model object itself. So switching back to the other template here, you can see that we'll continue on after the run is completed, and we'll read that model back in to score it. And then we'll get the predictions and our metrics, and then we can even generate that heat map that we saw earlier and apply it back to our run after the fact. This will save a lot of headaches for people and get people that maybe aren't as familiar with PySpark and deep learning started much more easily. So after we go through this exercise, you can see that we've actually improved our model just a little bit. We haven't changed the F1 score, but you can see in the two highlighted areas that we're not over predicting the majority class as much. We're seeing a lot better precision in some of the later stages here. So that gives us more confidence that we've got a better model. Okay, well now we're done, right? Data scientist work is all done. We can move on to the next project. Well, wait a second, maybe not. We have to register, score, and preserve the model to make it repeatable, and also help with deploying it to production. So the nice thing about MLFlow is that we can score it using a Spark UDF and read it in that way. And that way we can bring in a PySpark data frame to score it with pretty easily with just a few lines of code that you see here. Because we have so many Databricks workspaces, because our team is huge, we need to be able to set that up properly. So from there, we have the dev work done in their workspace, and they register that model there. They'll promote it to production status after that, when it's ready for review. From there, we'll take the MLFlow run associated with that registered model and use it to register it in our production workspace, where we hold our automated jobs all together in one space. This generates a single registry that can be used for all of our data scientists. We then will use that as the official version to do our automated scoring. We also have a helper function that allows them to generate a markdown set of descriptions for metadata for each of the models. We'll include the version and the path to the model so that we can have multiple versions running at the same time. To centralize things and to make things more reusable, we've set up a simple framework for NADF to deploy these models. We have 3 different notebooks: a feature engineering, scoring, and a score validation notebook. We also will check the dependencies here upstream of that if any other processes are needed to complete before these even start. This prevents the flow of bad data and errors from missing data from happening. We'll also log any failures or successes of this process using a SQL Server. By having the data scientists commit their model to a Git repo and allowing us to use ADO to be able to deploy these models, we can have them in various environments and have a lot more control over the versions and the parameters we input into them to allow them to run on different types of data. The partnership between data scientists and AI engineers is pivotal. All models are peer-reviewed for both domain and technical accuracy prior to production deployment. We have the teams inform us about new models early so we can schedule time with them to make sure they're on the right trajectory. As they work to prepare their model for production, we have a checklist for them to complete before deployment. And then we'll work with them to create the pull request and put that into the repo. From there, the AI engineers will help deploy that through the pipelines and make sure everything works before it goes into production. Each model is also initially reviewed and subsequently monitored for AI bias in key areas. We're the first major health insurer to take the Equal AI pledge, and this is an important aspect of our monitoring in production. So I'll document a few early wins from our time in the platform that's been just a little over a year. We scaled and automated a clunky on-prem manual process that involved creating 40 different condition flags. We now create over 3 times as many flags in the cloud and have gotten contributors from multiple teams following our templates. We now update over 1 billion rows daily in just an hour and a half for our entire member population. Another team experienced faster prep, more iterations, and better tuning and collaboration. We were able to reduce a feature engineering step from hours to minutes and enabled their data science team to iterate on models faster, with one run taking 5 hours on-prem, now taking a half an hour less, even for complex models. We also reduced the scoring step on prospective members from a week to 30 minutes. This allowed us to touch any aspect of the data science process, from feature engineering to scoring and training. We also have a lot of shared resources that accelerate everyone. Hundreds of features means less process duplication and more time to improve the model. We also have the flexibility to score at scale using those UDFs or pandas UDFs, regardless of the algorithm package. Thanks so much for listening. I hope you've learned something new and can take that back to your organization to improve model training and scoring at your organization like we've done at Humana. Thanks so much, appreciate your time, and hope you have time to review the session and enjoy the rest of the conference.